Alright, so in the previous video, we fixed this piece of tower geometry so that it can fracture properly without giving us some broken, errored output. So now let's explore some Boolean fractures. As I mentioned in some of the previous videos, Boolean fractures are the go-to technique for creating really interesting, convincing, art-directable fractures. That's because Booleans use explicit cutter input. So if we drop in a Boolean node, you can pipe in your geometry that you're fracturing in the first input, and then any arbitrary cutters you can place in the second input. However, this Boolean SOP does a lot more than just a fracture style shatter. If you select the Boolean and go to the help doc, you can find a good description of the various Boolean operations available to you in this operation parameter of that Boolean SOP there. And it gives you really nice diagrams to help you understand what those various operations do. In a destruction context, we're typically interested in the shatter functionality, so we'll focus on that. And you'll notice that if you type Boolean into our list of SOPs here, there are several Boolean options that pop up. Now, most of those will all drop the same Boolean node down, whether you do a subtract, or you do a shatter, or something else. All that's doing with those various options is setting your initial parameters differently. So when we create the subtract one, that means it's just setting the operation to subtract for convenience. But like I said, here we're mainly interested in the shatter. Out of all those Boolean options that pop up, the one that's a bit different is the Boolean fracture. Now, this one is using a Boolean under the hood. If you dive inside, and you can do this with many Houdini nodes if you're curious to explore what they're doing in more detail, you can dive inside and see that this is just using a regular Boolean shatter here, and it's just doing a bunch of other things for us for convenience. For example, it's helping us with the naming of our pieces, and it's setting the interior and exterior normal angles. As I mentioned in the Voronoi lessons, you typically want to set your interior and exterior separately so that you don't get some sort of weird interpolation at the edges. And it handles your interior and exterior groups. And at the very bottom here we have some of the same settings that you see on the standard Boolean node. Now, regardless of whether we're using the standard Boolean or the Boolean fracture SOP, we need some cutters to use to slice up the geometry. Now, you could, of course, hand place some noisy grids and spheres to put the cuts exactly where you want them, but let's generate this procedurally. After all, Houdini is awesome for its excellent proceduralism, so let's leverage that for our cutter generator workflow. I'm going to start with a bound SOP, which will just create a bounding box around our input. If you'd prefer, you can also perhaps use a shrink wrap, which will more tightly conform to the shape of your geometry. I'm just personally in the habit of using bound myself. And then I'm going to use an ISO offset node. And typically you'll see me use VDB from polygons for this sort of thing, but in this particular case we're creating a really low res volume. I'm just going to set the uniform sampling divs to 100. You probably don't even need to go that high. Even something like 50 should be enough, but I'll leave it at 100. And the reason I use this ISO offset sometimes, despite the VDB from polygons being better, is just because this has this built-in max axis option. So that will create a volume that's 100 voxels in size on every axis. Whereas the VDB one, if you just drop in VDB from polys, This uses an explicit voxel size, and it's a little bit more annoying to need to calculate our voxel size based on the size of our object. You'll notice that if we use this, then for a large piece of geometry, it might create a really high resolution volume that's kind of slow to compute. And we don't really need that because all we're using this low res volume for is to scatter some points in that area. So let's drop in that scatter node, hook it up to the ISO offset, and let's set the force total count to something really low. We'll just start with 10 for now. Maybe template our original geometry to see how they match up. And then we're going to copy some planar grids onto those points. So you can just create a grid and a copy to points node, hook up the points to the second input and the grid to the first, and you'll see 10 grids positioned in the object. Let's go ahead and make those a whole lot larger in size, like so. And then to randomize the rotations of each of them, we can just add a varying normal attribute to our input points. So this copy to points node knows to look for some predefined attributes on our input points to define how it scatters the objects onto the points. And one of those is just our standard normal attribute n. So we can just use our attribute randomize node, which is extremely helpful. And we can tell it the attribute name will be n. It's already doing it in 3 dimensions. And to tell this to randomize unit length vectors and random directions, we can set the distribution to direction or orientation. This has some other cool options for using cone angles and biases and etc. to control the direction, and that sort of thing can be useful for things like setting up particle systems, but we don't need to mess with any of those extra options because we just want these pure random normal directions. Now if we go to the copy to points, you can see that it has picked up those normal directions for our grids. Now our scattered grids are starting to look like some viable cutters, although we're going to need to make them a lot bigger and much higher res, because once we apply noise to them, we still want these cutters to pass all the way through the geometry. We'll talk about it a little bit more later, but anytime we have a partial cut that only goes partway into the geometry like this, it will create this strange surface inside the geo, and this might fracture okay as far as the Boolean process goes, but you won't be able to refracture it any further because these sort of partial cuts inside there will create some strange geometry that Houdini does not know how to refracture properly later. In fact, we can test this now. We can use these grids in their current state, and we'll drop in a Boolean shatter. Let's connect our original geometry and our cutters that we've made. And you'll see that the Boolean defaults to treating the first input as solid and the second as solid as well. I pretty much always use surface for my second input since these are, planar cutters. They don't have any volume to them. So we can flip that to surface and see what that result is. And you can see it looks like it's done the fracture properly. Let's test it with an exploded view to see what we get. And actually it looks pretty strange. There are so many partial cuts happening in there that it's not a very clean result. We're getting some pieces chopped out of there. But let's continue with this to clean up our cutters some more for a much better result than that. Alright, so once we expand our cutters a bit, let's try setting them to much higher than they seem like they really need to be. Better to go overboard and then trim them down afterwards. And let's amp up those rows and columns as well. Let's try a few hundred. and run our Boolean operation. This is going to go significantly slower with such high-res cutter geometry. But you can see now that those cutters are passing all the way through the geo, we're getting some much better results. It's still, very straight and angular because we haven't added any detail yet, but you can see it's working much better when we have those complete cuts.